Hi everybody, today's topic is equations of circles, Unit 1, Day 6. Our objective is I will be able to write the equation of circles. This is the last topic in our unit, so upcoming will be our Unit 1 assessment. Now the statement of inquiry is that a circle has shaped and continues to shape our foundational views on religion, architecture, culture, and science. The circle is a vital shape in both the very distant past and the present. It was often used to represent the divine and natural balance. It was the foundation to the creation of the wheel. Even now, the Large Hadron Collider is a circular tunnel due to the properties of forcing particles to consistently change directions and accelerate. And this was from an article written about circles from the Smithsonian Magazine. And I have 4 pictures that I want to briefly go over with you guys. The first one here is actually a house. It's called Solo House 2 and it's currently in Spain. And they use a circular design in architecture, both because I think it makes an artistic point and because they wanted to stretch and challenge what they can functionally do in a house in a circular way. The second one here are farm circles. They're circles that are created because of how water can get distributed to farms if you have large plots of land. And one way to do that is to have this huge, really long, rod thing that will be spraying water. It's like a sprinkler. And it goes all the way around in a circle. And so it creates these perfect circles that are beautifully green and well watered. And then land around them that aren't necessarily getting that same amount of water to look not as green. So then especially if you're flying over like on an airplane and you look down and you see all these perfect circles, now you know they're because of these watering methods. The Large Hadron Collider is a tunnel. It's perfectly circular. They do a lot of really, really important chemical reactions and physics experiments to discover a whole lot of stuff that I wish I knew more about. And then the last picture here is the oldest wooden wheel that they found in Slovenia. So you can see that from the distant past, from function and religion, all the way up to what we're doing now, whether it is agriculture, whether it's architecture or physics, circles are really, really important conceptually. But I want you to try something real quick. There's a little box. Try and draw a perfect circle. And I'll try 2. Maybe it'll look something like that. And I think most of you guys will see what I have drawn at least and say that is not a perfect circle, right? You can see this part right here is kind of weird. That part doesn't match up. It kind of concaves. I don't know what's going on over here. It's kind of wobbly, right? Most people will look at that circle and say, yeah, I guess it's a circle, but it's not a perfect circle by any means, right? But if you had another circle next to it, could you tell us which circle is more perfect? How would you know if it's more perfect? If you had access to different tools, what could you use? Maybe if you have a can, right? And you can draw by tracing around the can. There are other ways that you can create circles. I'm going to cheat a little bit, and I can draw a circle using my little tool here, right? And it'll create a circle for me. Now I want us to think a little bit more about what a circle is. And we're going to start with this diagram right here. I think most people will see that and say yeah, that looks like a circle. I think that is a circle. All right, and I want you to identify these 3 points that are labeled as A, B, and C. And I want us to see the relationship from the center, right, this middle section, we'll label that as M, from that middle point to A. So let's take a look and figure out what is the distance between A and M. Luckily, this one's just a straight vertical line, so we could use a distance formula, but we can also just count, and I think that will be faster in this case. So I'll go 1, 2, 3, 4, 5. So I know that line segment is 5 units. And we'll do the same thing with BM right here. And similarly, this one is also horizontal, so it goes 1, 2, 3, 4, 5. That one's also 5 units. Interesting. Now, let's take a look at point C. If we're going from C to M, we can see that that one is not a perfectly horizontal or perfectly vertical. It goes a little bit slanted, right? So if we look at point C, you can tell here, and also because of where our origin is, point C is 7, -1. And we can use a distance formula to determine that length. So if we're doing CM, we're going to use x2 minus x1 squared plus y2 minus y1 squared. All right, and then we're going to label this one as our x1, y1, x2, y2, and let's plug in our values here. 7 minus 4 squared plus -1 minus 3 squared. We know that gives us 3 squared plus -4 squared, 9 plus 16, square root of 25, which is a perfect square, and we get 5. Wow. So what we can see here is no matter from the center to any part of that circumference, the edge of the circle, we're getting these 5 units. And that's really important because it's actually the fundamental way that we define a circle. All right. So if we go from the center of a circle to any point on the edge of that circle, you'll find you can calculate it to be exactly 5 units, no matter where you're going, okay? Now, in a circle, we have 2 important segments that we talk about, all right? Both of which have to do with the center of the circle. So if we're going from the center to the edge, that value is always called the radius. And we have it in red right here. You could also have the radius over here, right? Or going through here or here, right? Anything from the center to the edge of the circle would be considered a radius. Now, the diameter is really similar, but it goes from one edge to the other edge of the circle, but passes through the center, right? So it's essentially double your radius. It goes all the way through like that, right? And we could go all the way through this way as well. Those are all your diameters. Now, when we have a circle inside a standard coordinate plane, we can write an equation that describes that entire circle, right? That outer edge of the circle. And the standard form of that equation is x minus h squared plus y minus k squared equals r squared, where our variables h and k represent the center. All right, your x and y represent just any point along the edge of our circle, and then our radius represents our radius. All right, so let's use this form and see if we can come up with the equation for the circle here in our first teacher example. What is the equation of a circle if the center is at 4, -2 and the radius is 7? So here, center, we always use this h and this k. It is the variables that represent the center of a circle. So here, we know that one's h and that one's k. And we know the radius, we usually use r, equals 7. So all we have to do is look at our numbers here, look at our radius, and plug it into our standard form. X minus h we know is 4. And then we're going to go y minus, and our k is -2. So we already have the minus from the equation, and then we have a -2. Squared equals, we know that our radius is 7. So r squared is 7 squared. X minus 4 squared plus y, and then minus the negative gives us a plus 2 squared equals 7 squared, which is 49. And that's your equation for the circle. So So take a little bit of time and try student example number 1. Now let's take a look at teacher example number 2. The center of the circle, 3, -4, and a point on this circle is 7, -2. What is the equation of the circle, and what is the radius of the circle? So here we need to note that there are 2 questions that are being asked, the equation and the radius. If we know the center, we label it H and K. And then if it's a point here, we know that's going to be our X and our Y. So like before, we're going to take our standard form, X minus H squared plus Y minus K squared equals R squared, and then plug in all of our known values. X is 7 minus H is 3 squared plus Y is -2 minus K is a -4 squared equals R squared. And we don't know what R is. We're looking for the radius. So we're just going to start simplifying this as we go. This is 4 squared plus negative minus a negative gives us a positive. So here we have 2 squared equals R squared. 16 plus 4 equals R squared. 20 equals R squared. Now here we have to recognize that R squared is different from R. In order to undo a square, we have to do the inverse operation, which is the square root. So I want us to remember R squared is 20 because that's going to be useful later on. But in order to solve for the radius, which is one of the questions here, we do need to solve for R. The inverse of a square is a square root, so we're going to square root both sides. The square and the square root cancel each other out, leaving us with R, and we get the answer to be the square root of 20. And if we simplify that into a decimal approximation, we get 4.47. All right, now we have one of the answers we're looking for. We know what the radius is, 4.47, approximately. But we also are asked about the equation. So we're going to go back to our initial equation, leave X and Y, plug in H and K, as well as our R value. So we have X minus 3 squared plus Y plus 4 squared equals, and we're looking for R squared. And look, we'd already solved for R squared previously. That's why I said this is going to be useful later on. So we can put 20 right there. And so that's our other answer. We have, this is our radius, and that's our equation. Take a second and try your student example number 2. All right, let's move on to teacher example number 3. Given this diagram, we're asked to determine the equation of the graph. So, I want us to find where are some points that we can identify on the circle. I'm just going to put some dots there. And then I'm going to count from one edge to the other edge. And I know that that's going to have to go through the center of the circle. All right, so that's essentially going to be my diameter. Just like that. So if I count all the way across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I know that my diameter equals 12, which means my radius is half of that, 6. Okay, that's important for us to know. Now what else I know is where our center is, right? If I go 6 over from either side, I'll get to the center of the circle. And I can find that coordinate point by going 1, 2, 3 in the negative direction, and then we're going to go up 3. And we know that our center is always H and K. So with this information, all we have to do, plug in everything that we know for our equation. X minus a -3 squared plus Y minus 3 squared equals 6 squared. X plus 3 squared, y minus 3 squared equals 36. And there we have our equation. So give yours a try as well. Now, as always, for our summary, we're looking for it to capture the main ideas, your main points of learning in 3 to 5 sentences. Making sure we're looking at how this connects to our statement of inquiry. And using our correct academic vocabulary. Thanks for listening, you guys.